Okay, to explain what what PCA or what NMF is doing, and it's fundamentally different than PCA. So here's how it goes. So this is sort of revisiting the experiment we did before with eigenfaces. So here's the original face. This is what we're trying to approximate. And in this case, we're approximating it with 49. So here we have the mean. This is the mean face across the data set. And then these are 48 different eigenfaces. So these are the eigenvectors that you get. And here we're reshaping them into little face pictures. And then these are the approximation coefficients that you use to approximate that desired face, and this is what you get. Okay, so this face that we reconstructed is definitely not a perfect match to the original. As you can see, there are some differences, but it does a reasonable job. The purpose here is mainly to explain how PCA is doing that approximation and how NMF is doing it, and to show how they differ. So again, when we look at these little pictures here, black means positive, white means 0, and red means negative. Okay, so these are our coefficients, these are scalars. So what this, to construct this face, we're taking the mean face, multiplying it by 1, and then we're adding onto that this eigenface multiplied by this small positive number, plus this eigenface multiplied by this small negative number, and so on, 48 times. So you can kind of see that when we're putting together this face, even though the face really is non-negative, we're not exploiting that, we're getting, maybe lucky with 49 different components here, that there's no red values here, no negative values. But you can see how, there's negative components that are being added to zeros and positive components, and at the end of the day, this is what you get. So what's different about non-negative matrix factorization? These are the columns in that first matrix. They're the building blocks or the dictionary elements. And then these are the non-negative combining coefficients. All of our dictionary elements are non-negative, and all of our combining elements are non-negative. And so we're taking this image times this, plus this next one times this, plus the next one times this, and so on to create our approximation. And what's interesting about it, as you can see now, is that the dictionary elements are just fundamentally different than they were in the case of PCA. In the case of PCA, these were relatively dense, meaning not that many zeros here, whereas in NMF, the dictionary components are all very sparse. There's just a few non-zero pixels in each one. And in fact, even these guys are pretty sparse. Maybe about half of them are significantly non-zero. And it's also interesting when you actually look at what you're building here. So when you look at different examples of these, you can actually see like the parts of the face you're reconstructing. So here you see like some eyes, like you even have like an eyebrow and an eye here. Or in some other cases, you have like a shadow under the chin, or maybe a shadow under the nose, or maybe a shadow to the right of the nose, or a shadow to the left of the nose. So these are your building blocks. In some sense, they're more interpretable than these guys. These guys are just kind of crazy looking. Okay, so people say that this is called a part space representation, which is very different than PCA is doing. So just some perspective on what NMF is doing. Okay, any questions on this? So let's just let's do just a quick summary comparison of NMF versus PCA, or they call this LSA in the context of text mining. So non-negative matrix factorization, you are approximating X by W times H. PCA, you're approximating it by US V transpose. Hey, both are low rank. Both are using a rank R. Now the difference is NMF is designed for non-negative x. In fact, if x has negative values, this whole thing doesn't really make sense. Whereas PCA allows any x. Non-negative matrix factorization gives you non-negative matrix factors, while PCA can have negative values in U and V. Also, NMF will give you non-orthogonal columns and rows here, whereas PCA gives you orthogonal ones. Non-negative matrix NMF encourages sparse terms here, as we saw, whereas PCA gives you dense terms. NMF turns out to be non-unique, whereas PCA is unique. And NMF solvers can get stuck in local minima, while PCA solvers don't. So there are a lot of differences between them. Different applications, you might want to use different ones. Let me show you another nice application of non-negative matrix factorization, which is recommender systems. So recommender systems are basically, the goal is to recommend products to users. So every time you go on the internet and you see an ad, there's a recommender system under the hood recommending that ad about that product to you. Okay, so this is like really big business stuff here. Billions of dollars go into designing these things. So, and one of the main approaches to building recommender systems is something called collaborative filtering. It's a specific design. And basically, non-negative matrix factorization is one of the main techniques for collaborative filtering. So this is how collaborative filtering works. Suppose you build a matrix X where the ith row and jth column of that matrix stores the rating for product I and user J. Okay, so you have only bought a few products, or at least the people collecting the data know only a little bit about you. Across products, and across products, they only know a little bit about all the users they know about. So what that means is when they try to fill in this matrix, it's mostly blank. There's just a few entries that they can fill out that are, oh, I know what this person thinks about that product. Mostly they don't know. But what they want to know is they want to complete all the values. Because once all the values in that matrix are filled in, then they know what you will think about any possible product. Right? You just look it up and like, oh, and then they look for the product that you're most interested in, and they say, that's the one I'm going to advertise to this person. So that's the goal. That's the setup. So these ratings are going to be positive. They're maybe numbers from like 0, 1, 2, 3, 4, 5, something like that. The point is that this matrix is incomplete. Okay, so only a few entries are known, the rest are missing. And so filling in the missing entries is a product called matrix complete, or it's a task called matrix completion. And the main intuition, or the main structure people use for matrix completion is they say, this should be a low rank matrix, meaning there's only a few kinds of users out there. There's many people, but we can kind of categorize these people into a few categories. And although there's many, many products, we can categorize products also into a few categories. And so what we need to do is just figure out what category you're in and what category that product is in. And now we have enough information to connect the dots based on other similar products that you have rated and other similar things other people have done. So that's kind of the intuition. And so the way that you do this is the math problem then, is, so this is the data you've collected. You only know this matrix at a few entries I and j. So when you form your loss, when you have this big sum over I and j, you can only use the I and j for which you know those entries. And then this is your approximation of x. This is a low rank matrix. This is basically tall times wide. You get to choose the rank, R. So if you choose the rank R too small, then you have sort of a bias problem. You just you're coming off too simple of a model to capture all your users and products. On the other hand, if you make R too big, then maybe you just don't really have enough data to really fit this well. So you have to choose R well, but other than that, the other key thing here is when you do this minimization, you are assuming that you have positive W and H. And so one kind of approximate way to do this is you just fill in, you take your matrix X, which has a lot of blanks. For all the terms that are blank, you fill in like a constant mean value, for example, that is like the average of the X values you know about, and then you just do non-negative matrix factorization directly to that. So there's all kinds of tricks and approximations to solving this. There's also much more sophisticated approaches, but at the end of the day, this is related to non-negative matrix factorization because the approximation is based on that idea. So one of the famous examples of this, the most famous examples, is the Netflix contest. Have you guys ever heard of that? So the Netflix contest was, I don't know, maybe it was like 10 years ago or so. Netflix gave $1 million to the winner who could come up with the best recommender system based on its movie data. So they had a big X matrix that had 18,000 movies in it, 480,000 users. And if you multiply those two numbers, you get a number that's close to 10 billion entries in the matrix X. But they only had data for 100 million ratings, so basically 1% of the matrix was complete, 99% was incomplete. And then they were looking for schemes that could complete it. They probably had test data. They probably split what they knew into two folds, a train and test, and then they gave the contestants the training and they measured how well they did on the test and saw who did best. Probably something like that. Okay, but it's kind of a neat thing. So this is the sort of thing, like if you're talking to someone that doesn't know anything about machine learning or math or anything, and they ask you, what are you doing, or what is this about? You could tell them about a problem like this. It kind of makes sense to everyone. Okay.
Was that a public contest?
Yeah, it was public, definitely. Yeah, there's a green. If you click on the green link there, you can see the details.
14 years ago.
What was that?
It was 14 years ago. They were still doing DVDs
14?
back then.
Yeah. So. Okay. So. All right, so that kind of finishes what I wanted to say about matrix factorization. So now we're going to switch gears to another very different approach to clustering that is more statistical instead of about matrix properties, algebra. And the idea is Gaussian mixtures. How many of you guys have heard of Gaussian mixtures? Okay, so let's start at the beginning and let's talk about just a Gaussian. So if we have a single Gaussian in more than one dimension, so in one dimension, as we know, a Gaussian is like a bell curve. If you have a Gaussian in two dimensions, it looks something like this. It's like a bump, right? And the center of the bump is going to be the mean of the Gaussian. So in terms of this is the probability density function. So the mean would be mu. And everything else apart from where it's centered, basically like how is this stretched in those two directions, that is determined by the covariance matrix Q. Right, those are the only two parameters of this distribution, is the mean and the covariance matrix Q. And when you look at this expression, just remember that, to interpret this, basically you have a quadratic form here, which is, you guys have seen a lot of things like this. This is just an exponentiated quadratic form, so that means that this thing has sort of quadratically decreasing tails, but then when you put it inside an e to the minus, they drop off really quickly. And all this is a scale factor, so that when you integrate this, it integrates to 1. That's really, focus on, in terms of the structure of it, just focus on kind of this part here. Okay, and we're going to abbreviate this by script n, that means Gaussian. X is the variable of the Gaussian, mu is the mean, and Q is the covariance matrix. Okay, so So the interesting thing about these Gaussians is that when you look at these level sets of equal probability, these sort of things here, they are ellipses. They're ellipsoidal. And as we know with an ellipse has a principal axis, or two principal axes. One is like the major axis, one is the minor axis. And if you want to know what those are, the directions those are, you take an eigendecomposition of your covariance matrix, just like what we did with PCA. And the eigenvectors are exactly the directions of the principal axes of your ellipses. And as we know, they must be orthogonal, right? And that's also true for ellipses. This is ellipse in 2 dimensions, would have those two. You can imagine ellipse in 3 dimensions. It kind of like it's like that in 3 dimensions. You would have 3 different orthogonal directions of the principal axes. Now, in terms of how they're stretched, like this one you can see is stretched in 1 dimension more than another. They're stretched by the inverse square root of the eigenvalues. So that is exactly the lengths of these different things. So if you have a small eigenvalue, when you invert it, it gets large, right? And that means that you have a wide spread. So that kind of makes sense. Like if you think about the covariance matrix, if the variance is small in a particular direction, that means it's spread large if the variance is large. So how does this work? So if the eigenvalue, which is like the variance, is large, then when you invert it, it becomes small. Somehow I'm getting tripped up here.
Is it less than 1? Is it the square root of something less than 1?
I think it's because it might. So somehow the inverse is coming into play. It might be that this is of the inverse. Okay, I'll have to think about this. But basically, the moral of the story is, if you know the eigenvectors and eigenvalues of the covariance matrix, you can say exactly how these ellipses are oriented and stretched. Okay, and so like one example is, if you have an if you have a covariance matrix that has, what would it be? Well, okay, let's. Okay, so that's sort of what we have with a single multivariate Gaussian. Okay. Now, that's not really useful for clustering because in some sense, this looks like a single cluster, right? When we think about clustering in terms of little collections of points. So it becomes more interesting when you have a Gaussian mixture model. So it would be like if you have data that seems like there's 2 different clusters with ellipsoidal, some sort of density that looks ellipsoidal. You can model each one as a Gaussian, but the fact that there's more than one Gaussians makes this a Gaussian mixture model. So in terms of the PDF is going to be the sum of scaled Gaussians. So if you had this in a single dimension, that means you'd have like one Gaussian here and another Gaussian here. But the data, the data kind of is most probable to be around here, around here. And in 2 dimensions, looks kind of like this. So when we look at these ellipsoids are going to be, well, first of all, the location of this cluster is going to be determined by the mu corresponding to that cluster. So maybe this is, for example, this could be k equals 1. This could be k equals 2. So then the mean right there would be the vector mu1. The mean here would be the vector mu2. And then the way that these are stretched is determined by the eigenvectors and eigenvalues of q1. The way that these are stretched is eigenvalues of eigenvectors of Q2. And there's one more parameter in this model which reflects the fact that it could be that maybe most of your data goes here and only a little bit of your data goes here. So that's what these weights do. The weights here have to be non-negative and they sum up to 1. So, so the weight tells you essentially how likely it is for the data to land, in this cluster versus this cluster. Okay, so basically that's a Gaussian mixture model. You can use them for many different things. Many different data sets are well modeled this way. But our interest in this unit is to basically apply this to clustering. So at a high level, it goes like this. You're given a data set, X. Your first job will be to figure out the best setting for all these parameters in your Gaussian mixture model. So we're going to do that using maximum likelihood, as usual. But we're going to learn a new tool to do this called the expectation maximization algorithm, which is going to work a little bit better than something like gradient descent. We'll talk about that mainly on Friday, I think. So that will be something we'll have to spend some time on. But imagine that we've done that, and now I know all these parameters. Then, essentially, if you give me a new point X or any existing X in your data set, you would plug it in here, and you would like to somehow evaluate, okay, if you hypothesize like k equals 1, how high is that likelihood? Or if you hypothesize k equals 2, how high is that likelihood? So it's sort of like, given a point here, you could say, is this closer to this in the sense of probability, or is this point closer to this in the sense of probability? So that's sort of the high level, but we have to understand that a little bit better, like understand exactly all the calculations that go into determining which GMM component is more probable. Okay, so to do this, we're going to think about things in a slightly different way, which is what they call a hierarchical view. It's like a two-stage approach, and I think maybe the easiest way to understand it is to say, let's say that someone gave you this distribution, and they said, generate points from this distribution. So like, they give you the statistical model, and then they want you to generate random points like this. Okay, so the way you could do this is you could think about this in two stages. First, you could say, which mixture is it coming from? We're going to define the mixture index by kappa. And then once you determine which mixture it's coming from, you can simply focus on that Gaussian and then just generate a Gaussian random variable. So it's splitting this into two easy problems. Okay, so when you think about which mixture it's coming from, we really have these variables that guide us there. So this is, we have different lambdas, different gammas. All the gammas are non-negative and they sum to 1. So if you just think about those gammas, they define a probability mass function, a PMF. Okay, so we can create this PMF, and that PMF just tells us the probability that a data sample comes from mixture 1 or mixture 2 or all the way up to mixture K. Okay, so given that PMF, and so this is the official definition, the probability that kappa equals K is gamma sub K. So that's a pretty straightforward thing. If I give you like a vector of probabilities with a few lines of code, you can figure out, you can like generate a random number between 0 and 1, and then kind of threshold it, see which bin it falls in among those different levels. And then you could say, okay, if it falls within this bin, I'm going to, declare it to be a, If it falls in one bin, I'll declare it to be from kappa equals 1. If it falls in the next bin, from kappa equals 2, and so on. And the sizes of the bins are proportional to these gammas. Okay, and then the second step is also relatively straightforward. Given that it's coming from bin kappa, now the PDF is Gaussian with variable x, mean mu kappa, covariance q kappa. So, and there's pretty easy ways to generate Gaussians. Okay, so I won't go into those details, but basically we're splitting this thing into two simpler steps. And explicitly, you would say the probability density of X, given that it came from when kappa equals K, that it was generated from the kth mixture component, is Gaussian with these parameters. Okay, so that's a way to break this up. And so this is sort of kind of a heuristic explanation that I gave, but you can also construct this just with probability. So let's see how that works. So if I start with P of X, for any P of X, what I could do is I could stick in a new variable, kappa. And this is the law of total probability. Maybe it's easier to see to go from here to here. If you have this joint density and then you integrate out, or in this case, because it's discrete, you sum out one of them, then you're just left with the other one. So this is the law of total probability. The next step is to write this joint probability as a conditional times a marginal. So this is probably something you guys learned in your probability class. P A comma B is P A given B times PB. So that's all we're doing there. And finally, we can interpret these things. We said before the probability of X, given that it was drawn from distribution K, is this Gaussian one, and the probability that kappa came from K is gamma K. And now you can see that this exactly matches what we set out, how we described it at the beginning. Okay, so just sort of like explaining it a little bit in a more direct, principled way. Okay, so the idea is think of this GMM as a two-level hierarchy. First draw kappa, then draw X given kappa. So what's interesting about this approach is there is no kappa here, right? Kappa is something we actually kind of made up. Made it up just to make our lives easier. And this is something that happens a lot in statistics. Sometimes it helps to come up with what's called a hidden variable, something that doesn't explicitly appear, but it's just like a helper. There's many ways of doing this, depending on the probability density you're working with or the task you're trying to solve. So in this particular problem, the best choice of hidden variable, the most convenient to us, is to set kappa to be the mixture index. Okay, but this is definitely not the only way to do it. All right, so any questions on Gaussian mixtures? Okay. All right, so now that we have this kappa identified, it's maybe more clear that this is exactly the thing we care about when we cluster. So this is what we just came up with. Probability of X is a sum over the different cluster or component indices K. The probability that this hidden variable is K, and the probability X given that hidden variable. So when you think about it, the hidden variable kappa is really telling us this information about where that X is coming from. So the thing we care about when we cluster is we want to figure out what is the probability of kappa given X. So we're given this point X. We have this model, but what we don't know is which kappa, which cluster X came from. So can we figure out the probability? So that's the goal. And the answer is yes, we can do this with Bayes' rule. So we saw Bayes' rule before when we talked about lasso. Bayes' rule, the way that it works is, or the reason you tend to use it is when you have a conditional probability and it's inconvenient, and if you could just swap it, then you could make sense of it. That's one of these cases. So we're going to swap these with Bayes' rule. And so Bayes' rule says, okay, when you swap it, you get X given kappa, but then you have to multiply it by the probability of kappa, and then you have to divide it by the probability of X. Okay, but the main thing we've accomplished is we've rearranged this. And the reason we're doing this is because this is something that's easy. Right? We know the probability of X. If you tell me kappa, that's just this. That's just a Gaussian. Also, we know the probability that kappa comes from K is just gamma K. Okay, and then this PX, PX is basically Px is this whole thing. So I can just plug that expression into the denominator. Okay. And I'm just going to use a variable kappa prime to not confuse us because, k prime, because k is actually has a specific meaning on the left side. So, and that's the same k here, but the k on the bottom is really a different k. So this is just a temporary variable k prime. Okay. So when you do this, if you can compute this, which, let's say we fit all our mu's and q's and gammas, we can just plug x into this expression. We'll get a number between 0 and 1. And that's what we call a soft assignment. So we hypothesize what about k equals 1? You compute, maybe you get 0.1. Okay, probably not coming from k equals 1. So then you try, what happens if k equals 2? You compute this and you find, oh, now it's 0.9. Okay, that's probably where it's coming from. And so those are the soft assignments. They give you a confidence in these different hypotheses of which cluster it's coming from. But at the end of the day, you may just want to say, no, I don't care about all those numbers. I just want you to tell me which cluster. Just give me one cluster index. So that would be the hard assignment. So it means you look through those probabilities and you just find the index of k that gives you the maximum probability. So this is very similar to what we did with classification, right? We did the same thing. We computed, like out of a softmax, we basically got stuff like this. And then we came up with the hard classification at the end of the day. Okay, so those are the main things we do for clustering with Gaussian mixture models. Evaluate the probability kappa, the soft assignment, and then finally, you can say quantize it. We'll call it kappa hat. So this is going to be a number 1, 2, all the way up to k. Okay, so that's pretty much it. So here's a summary of the procedure. So someone gives you a data set of xi's. First task, which is kind of the hard one, is to find the Gaussian mixture model parameters that best fit this data. So for all the different clusters k, you have to figure out the gamma, the mu, and the q. Now that you've done that, for each data sample I, and for each hypothesis of the cluster k, you compute that soft probability. What's the probability that xi came from the kth cluster? And so we know how to do that. We compute this. So we have to do that for all these different cases. And then for each sample I, we can compute the hard assignment. We say for that assignment, or for that I believe that came from this cluster. And that will finally give us the colors that we see here. So there's basically going to be some decision boundary. It's not going to be linear anymore. It's going to be maybe something that looks like this. And so anything on this side will come from that cluster, and anything from this side will come from that cluster. So that's basically how we do clustering with Gaussian mixture models. Okay, any questions on that? Okay, so now the slightly harder part is fitting the Gaussian mixture model parameters. So as always, we use maximum likelihood. Okay, so what does that mean? It means find the thetas that maximize the probability of our data, x, all these guys, given that hypothesis of parameters theta. We also know we can maximize the log likelihood, and that's often easier. And in this case, the log likelihood is a bit difficult to work with. So we know we always, assuming independent samples, we always have a sum over our samples on the outside of our log likelihood. But now we're going to have the log of this sum of Gaussians. If we had only one, the log of a Gaussian is very nice to work with, right? Because when you take the log of a single Gaussian, you get log of this, and then cancels the exponent, and you get a quadratic form. That's really nice. It's not nice when you have the log of a sum of Gaussians because you can no longer do that. This sum ruins all of that. You're stuck with this, and you have to figure out a way of working with it. There's cases where people approximate this. They might approximate this. What they'll say is, let's just find the largest Gaussian and then ignore all the other terms in the sum. But that's kind of a gross approximation. We don't want to do that in this case. Okay, so we have this difficult problem. You could do something like gradient descent. You could take gradient steps, I guess uphill, maximizing the likelihood or the log likelihood. But that would be pretty slow, and it would probably get stuck in a really bad local minimum. So that's not the approach we're going to use. We're going to use a new approach called the expectation maximization algorithm, which is a super powerful algorithm that is used all over the place. And it is a bit more complicated than other things we've seen. So bear with me as I try to explain it from different perspectives. Okay, so first of all, at the highest level, what is this? What is this EM algorithm? It's an iterative approximation to generic maximum likelihood estimation. So anytime you're doing maximum likelihood estimation, the EM algorithm is always one possibility that you can use. So gradient descent is another, but EM is usually much, much faster, much more efficient. It is more complicated, so there's that burden. And it can, so what can you say technically about it? It's guaranteed to converge to a local maximum of the likelihood, which is good, but it can get stuck in a bad local maximum. It can happen, so you do have to try to give it a good initialization. So it's not a cure-all, but it often works pretty well, so it's definitely used quite a bit. And EM algorithm is also based on hidden variables. So it's kind of a natural fit. We have this Gaussian mixture model with hidden variables. EM algorithm is also based on hidden variables. And like before, hidden variables are very generic things. There's many ways to choose them for different problems. So depending on the problem, you just have to make a good choice. But for the moment, we're not going to talk about clustering. We're going to try to be totally general, and just imagine that we have some likelihood, some log likelihood, and we have some hidden variable z, and we have some parameters theta that we're trying to maximize. Okay, so this algorithm proceeds in two steps, what's called the E step and the M step. This is why it's called the EM algorithm. Okay, in these steps, the E step involves an expectation, and the M step involves a maximization. So that's why E and M. Okay, so we have to kind of dig into these because it's a little bit complicated what's going on. So remember that whenever you have an expectation of some quantity, that means essentially you're taking that quantity, putting it inside an integral, and multiplying it by some PDF over some variable. Okay, so this is exactly what's going to happen here. So here's the quantity that we're taking the expectation of, so that appears here. And this is telling us about what kind of expectation we're going to be doing. We're going to do an expectation on z, but it's going to be a conditional expectation. That's going to be conditioned on our data, which makes sense because our data is just what we know. And it's going to be conditioned on the iteration t guess of our parameters theta. So this little subscript t means that's our guess at iteration t. And so here is that conditional expectation inside this integral. And so this is just shorthand notation for this guy. Okay, so now a little bit more intuition. Okay, what's really going on here? So this probability is telling us, it's telling us information about what we know or what we believe about the hidden variable z, given our data and given our current guess of our parameters. So let's take an extreme example. Let's say that given my data and given my current parameters, I was absolutely certain that z takes on some value z hat. Let's just say I'm totally confident. So now let's say if that's the case, we can plug this in. This is a Dirac delta. How many of you guys have heard of the Dirac delta? So yeah, good. So if you take 5200, you see this. So this is like a spike that has unit area, which is important because it's a PDF, but it's like an infinitely tall, infinitely narrow spike that is centered at z hat. Okay, so if I plug in this PDF into this integral, due to something called the sifting property, essentially the integral vanishes, and I get this. Okay, so now we can sort of make sense. What is this Q thing in that special case? It's just the log likelihood of x, but evaluated at your current guess of your hidden variables. right? So if that was the case, you would then be saying, okay, my next job, given that, is just to find the theta that maximizes my log likelihood of x, given my current guess of my hidden variables. Okay, so I think that kind of makes sense. Now, this is sort of an approximation because in practice, what's really going on here acknowledges the fact that you don't exactly know what z is. If you really, said, I'm absolutely confident about this, you'd probably be wrong. And that would be probably too overconfident. You'd probably get stuck somewhere. You actually have to embrace the lack of certainty you have about your hidden variables at every iteration, kind of exploit that. Well, it could be this, it could be that. And this PDF is actually telling you exactly the shape of your uncertainty. So rather than plugging in this thing that's absolutely confident, which would give you this, you're saying, I'm going to acknowledge my lack of confidence, and instead of this, I'm going to use this more general thing, Q. Okay, so it's similar in spirit to this, but it's acknowledging the fact that you don't exactly know your hidden variables. You have some knowledge, and that knowledge actually changes with the iteration T. As you go with iterations, you get more and more certain about your hidden variables, but when you start, you're very uncertain about them, and you don't want to be overconfident. Okay, so that's kind of some intuition about what's going on sort of at a high level in here. Okay. There's some other ways we can understand this, which I think are very powerful, but are there any questions so far on this? Okay. So this is kind of the more thorough explanation, which is based on a lower bound argument. And so it goes like this. Let's say we have our log likelihood. This is the thing that we want to maximize, right? We want to find the thetas that maximize this for our fixed training data x. But this thing is really difficult to work with. For our current problem, this is a Gaussian mixture model. It's hard to work with. So we're going to try to come up with an easier way to work with it. So the first thing we're going to do might sound kind of strange. So we have some hidden variable z. We dreamed those up. And then let's say that we have some belief on what those z are. This is going to come from some PDF that we're going to call p hat. It's our belief on z, right? And I can write my log likelihood like this, simply because I'm integrating over z. This guy has nothing to do with z, so I can pull this out of the integral, at which point what remains is this. And for any valid PDF p hat, I know it integrates to 1, so that thing goes away, right? So hopefully you can see why these things are equal. They're equal in a very weird, trivial sense. This is definitely true for any z, for any PDF p hat. So this is like, why are we even doing this? Okay, it gets more interesting. So now we're going to do something that's totally non-intuitive, which is to expand this log into something that's much more complicated. So I'm going to try to convince you that this second log is in fact equal to the first. Okay, so to see this, first notice that these will cancel, so you can forget about them. What about this other stuff? Okay, so let's look at this. So pz comma x divided by pz given x. Okay, this is a weird thing. Let's make sense of this. What we can do is we can write the top, similar to the last page, as z given x times px. So do you remember how you can always write the joint as the conditional times the marginal? After you've done that, now you can see these cancel. And so in fact, this really is equal to p of x. Okay, so hopefully you can appreciate that, yes, this is true. Still not clear why we're doing this, but at least it's true. Okay, so now the more interesting part. So when you have log of a product of stuff, that's like, you can write that as a sum of logs, right? So what we can do is we can write this as log of this top p, which is here, minus log of this p hat. Here's minus log of the p hat, plus log of this. Okay, and that's log of this. Okay, and then, so basically we have a sum of logs here And they're all integrated in the same way, so I'm just going to get a sum of these three integrals. Now, there's actually some meaning to these quantities. The last one is the most important. So this term, this is called the Kullback-Leibler divergence. This is something that shows up in information theory. But basically what it is it's a way to compare two PDFs. If somebody gives you two PDFs and they want to say, are these similar or different? Like, give me a number to express how different they are. The KL divergence is probably the most common way to do that. So let's look at this. Let's say the two PDFs were the same. If this guy equals this guy at all z, their ratio would be 1 for all z, right? And then the log of 1 is what? 0. So then this would be 0, the integral would be 0, and the divergence between these two distributions would be 0, right? So basically that makes sense. If you give me two identical PDFs and you ask me how different they are, the difference is 0. It turns out that it's not as easy to see, but for any two PDFs, no matter what, this quantity will be positive. So any differences in the PDFs will actually manifest as a non-negative thing. So it really is a way to compare two PDFs. Like I said, there's different ways to do that. This is probably the most commonly used one, called the KL divergence. So the key thing that we know about this last term is that it's greater than 0. And we're going to use that in just a moment. Just for the sake of understanding the middle one, this one is the definition of this. This is the entropy of this distribution. So as you've probably learned different places, entropy is just a measure of randomness, a measure of uncertainty in some sense. So if you give me a distribution and the distribution is very concentrated, then it's going to have little entropy, but if it's very spread out, it has more entropy. So just sort of a measure of the entropy of this p hat. And this just gives us a way of like intuitively understanding maybe what that is saying. And then this last one, maybe it's not as intuitive as to the meaning of this. It's the expectation over some belief of this log joint distribution. So it's a little bit weird, but maybe the key thing is that we've actually just seen this. That is exactly this. This is the expectation over some belief on z of the log of the joint. Okay, so this is, as you can see, is starting to get related to the EM algorithm. This is, in fact, the main quantity in the E step of the EM algorithm. Okay, so everybody with me so far? Okay, so the most important thing here is that because this is positive, it means that if I throw this away, that the right side gets smaller, right? If I throw away a positive thing, the right side gets smaller. And at that point, what remains will be less than or equal to the likelihood. So that means it's a lower bound on the likelihood. This is what remains after I throw away KL divergence. This is a lower bound on the log likelihood. Okay. And we're going to give this lower bound a name because it's important. We'll describe it as script L. And it's going to depend on p hat, which is the density or my belief on my hidden variable z. It's going to depend on that. And it's going to depend on our parameters theta. Of course, it also depends on our data set, but we're just going to omit that from the notation because everything depends on the data set. Okay, so we have the log likelihood is lower bounded by this term here. And the way that we can understand the EM algorithm working is that it iterates two steps. First, it chooses p hat to tighten the lower bound, meaning let's make these two sides as equal as possible. Let's, try to make this maybe an equality. Okay. And then second, it's going to choose theta by maximizing what remains. Now you can see that this term doesn't depend on theta, so maximizing theta we can do just with this. So that's, again, closer to what we're doing. We're maximizing, we're maximizing this expected log joint. That's what we're saying is happening here. And then the very last thing to explain is this tightening. Why why does the EM algorithm choose the p hat that it does? Okay. Before we get into that, let me just show you maybe another intuitive picture. Let's say that my log likelihood is this one. So this is x. That is theta. This is theta. Let's say I just have a single parameter I'm trying to decide. So I'm trying to pick theta. This is my log p of x given theta. So ideally I want to find this value. But let's say that this is kind of difficult to maximize. And in fact, imagine that you tried to attack this problem with gradient descent. What would happen? So let's say you initialize somewhere over here with gradient descent. What you would notice is you'd say, okay, what's the slope here? Well, it's positive. Its slope is this. So you take a step to the right. Maybe it's a small step, maybe it's a big step. Eventually, maybe with many small steps, you get over here. And now you say, oh, my slope is negative. So now I'm going to take a step to the left. And if you use the same step size, what would happen? You'd bounce back and forth, never settle anywhere, right? So this is in part because this is not a differentiable cost function. So this is one of the sorts of cost functions or utility functions that will give you trouble with gradient descent. The solution to that with the gradient descent is to shrink your step size over time. Then eventually it would bounce less and less. You'd get there, but there's other approaches to this problem that are sometimes more efficient, and this approach here we're talking about is one of them. So what's happening in this approach is we're coming up with a lower bound on this curve, and the lower bound that we've constructed in this case happens to be quadratic. What's nice about quadratics? What's one thing that's nice about them? If I want to minimize a quadratic, pretty easy, right? I can do it in closed form. And so here, if my lower bound is quadratic, then this minimization, or actually maximization, this is a concave quadratic, the maximization is super easy. So let's say that I start with my initial guess here. The first step is to figure out the quadratic that is a lower bound, that is the tightest lower bound at my current guess. So I'm going to find the quadratic that touches here, but otherwise is strictly below my likelihood. Now, next step, the M step, I maximize my quadratic. So I find the theta that maximizes this, which I can do in closed form. It's where the peak is. And now I start over. Now I'm here. Now I find a quadratic there. I maximize that. And that's my next theta. Then I find the quadratic, here, and so on. And you can see how if I iterate this, I will eventually move up to the top. So iterating between tightening the lower bound, optimizing it. Tighten, optimize. This has a name. It's called majorization minimization. It's a pretty common approach in optimization. It's when you iteratively tighten and maximize a lower bound. Okay, so the EM algorithm is a special case of majorization minimization. You can find many other examples of majorization, minimization, and optimization, but EM is just one of them. Okay, but it helps us explain what's going on. So concretely now in EM, this is the thing we're trying to maximize. This is the lower bound, which has this E log joint plus entropy. And then this is the term, the Kale divergence, which we know is non-negative. And this guy is responsible for any difference between this and this. Right? The larger this is, the bigger the difference between the true likelihood and the lower bound. Okay, so if we want to tighten this approximation, how do we tighten it? What's the tightest possible? These are equal, right? When those are equal, this must be 0. How do I make this 0? By choosing p hat. Can you see it? What's the p hat that makes this 0? This, right? So, and I know this at every iteration. So what I do is at every new iteration, t plus 1, I set my belief on z according to this particular conditional PDF. Okay? So the tightest bound occurs when the KL divergence is 0, or by choosing this particular p hat, and that's exactly what EM is doing. So coming back to EM, this is the p hat that it chose. That's it. So that's the last piece in the puzzle. So basically this, there's some expectation over some p hat. To tighten that lower bound, it chose the best possible p hat, and that's where you get this Q. And then the next step, as we saw, is just maximizing this thing over theta. So this is the theta that is a free variable. This is not a free variable. This is the theta that was our previous guess. So when we do the maximization, we're maximizing over this, not over this. Okay, so that pretty much explains the EM algorithm. So use this tightest bound. And then the lower bound maximization, again, this is our lower bound. We want to maximize this over theta. Well, this has nothing to do with theta, so forget about that. Just maximize this. And this is the p hat that we used here. Okay, so finally we have EM. And okay, so sorry I went over time. What we'll do, the only thing left to do is to go through and show exactly how we apply EM for our Gaussian mixture model. So we'll go through those equations next time, show a nice demo or two about how well that works, and then we'll be done for the semester. So see you guys on Friday. Oh, question? Yeah.
Is there a quiz on this unit? And
Yeah, so there will be a quiz, and it will be on, so it will be assigned Friday, and it will be due, I'm trying to remember, sometime before the end of the term, like, I'll send out an announcement.
Okay.
Yeah. So the last day of class it's next Tuesday? Next Monday, okay. And your projects are due Tuesday, right? So, I don't know, when would you want the quiz due? Thursday?
It's automatic, the grading of the quiz.
Yeah, I guess it's fine if it's due after the last day of class. Yeah, it's fine. Okay, could do it after the final, so you could, final project, focus on that.
My other question is, in terms of like the slot that we have for our finals, like, are you doing the casual competition live or anything? Or
Oh,
is there,
no.
like, reason to come in the?
No. So like at midnight, Wednesday morning, basically it's like all automated. So Kaggle will release the
Okay.
the leaderboards showing the private fold, and everybody's ranking on that.
Gotcha.
Yeah. So there will be no fanfare. No.
Well, we just come in and watch the screen.
Yeah.
Okay.
Okay. All right. I hope your projects are going well. See you guys on Friday for one last lecture.